Hey YouTube, Booth Dog again. Here we are, Tuesday of our second week of this new experience for us all. Hope you're doing well. Continue to reach out to me if you need absolutely anything. Before we get started for today, just want to point out that today's video is sponsored by pencils. Lots of pencils. And not those trash mechanical pencils either, but real wooden pencils that actually work. Now, since some of you have started complaining about the lack of, shall we say, decent editing in some of these videos, I guess I'll capitulate. Let's bring on Mr. Boothman and get started. All right, let's go. Good morning, happy Tuesday. Let's go ahead and jump right in. This is the last new section of Unit 7, Vectors. 7.4 is all about applications of vectors. So how can we use these vectors to solve real-world problems? Quick announcements to start our day. Your exit ticket today will be, just like last Friday, to submit a question you have from today's lesson. This will be due by midnight tonight. Let's go ahead and jump in. So section 7.4, as I just said, is all about applications of vectors. There's a lot of real-world situations where we use vectors. We're going to explore a few of those situations in this section. Today and tomorrow we'll really just be going through a couple of examples each day. Thursday will be practice exit ticket. Okay, so that's what the rest of this week kind of looks like. Looking at our first application of vectors example, we're talking about velocity. So reading our example here, an airplane heads due north at 300 miles per hour. It experiences a 40-mile-per-hour crosswind flowing in a direction of 60 degrees northeast. All right, so for all of these questions, all of 7.4, draw a picture of the situation. Please. Vectors especially, it's a very visual thing. So please, please, please draw pictures. So we have an airplane heading due north at 300 miles per hour. We'll call this vector V. Due north at 300 miles per hour. 300 miles per hour, that's the magnitude of this vector. Okay, that's the speed. So we know that magnitude of vector V is 300. It experiences a 40-mile-per-hour crosswind flowing in a direction of 60 degrees northeast. Now, we've talked about bearing and direction before. This is kind of a weird way to write it. It's not quite what we practiced. On all of your assessments, I am always going to express a direction like this in this way. So instead of saying 60 degrees northeast, we have this wind that's flowing north 30 degrees east. Notice that is the same thing as saying 60 degrees in the northeast direction, but that's just not a way of expressing direction that we've practiced very much. So I'll keep it consistent. Okay, so this would be 60 degrees. And let's call this vector, I don't know, U. All right. Now vector U, it says, is flowing at 40 miles per hour. So that means we know magnitude of vector U is 40. All right. Express the velocity of the airplane relative to the air and the velocity u of the wind in component form. Okay, so this question has quite a few steps to it. We're going to do it one step at a time. Let's just start with the easy one. So part A, velocity v of the airplane in component form. So that means we need A and we need B. There's a couple of ways to approach this for the airplane's velocity vector. I'm going to do it the more complicated way, and then I'll show you hopefully how you can just recognize what the answer should be. So we know that A, the horizontal component of a vector equals the magnitude times the cosine of the direction of the vector. And then b is the magnitude times the sine of its direction. So our magnitude for the velocity vector of the plane is 300. And what is the direction? What's the angle here of v? Well, it's just a right angle. It's going due north, so 90 degrees. What is the cosine of 90 degrees? It is 0. So our horizontal component is 0, and the sine of 90 degrees is 1. So our vertical component of velocity v is 300. So our velocity v vector is 0I plus 300j. Now, that was using our formulas. You know, we should work every time. Hopefully you also recognize that, well, this vector is just going due north. So does it have a horizontal component? No, that horizontal component is 0. All of the speed of this plane is going northward. So it's all in a positive vertical direction, 300. To find u, it's the same idea. But now we're dealing with the magnitude of vector u, and we need the direction of vector u. Vector u is going in a direction. Okay, remember it's an angle in standard position, so 60 degrees. What is the cosine of 60 degrees? 1/2. The sine of 60 degrees, square root of 3 over 2. So in component form, the wind's velocity vector is 20I plus 20 square root of 3j. And that's it for part A. Okay. So breaking up, this is quite useful because now it tells us exactly how much of the wind and the plane's motion is going in which direction. So broken up just like this. The next question is where things get kind of interesting. So I am going to rewrite these vectors over here. So I can erase all of this. Find the true velocity of the airplane as a vector. Okay, well, what does that mean? So this plane is flying due north. Okay, that's where all of its motion is going. But there is this crosswind that's pushing it toward the northeast. So the actual velocity of the plane isn't going to be due north. It's affected a little by how much the wind is pushing it. So its true velocity vector is going to be vector u plus vector v. I'm going to call this vector w. This is the actual velocity vector of the plane. It's not just being pushed by the wind, and it's not just moving due north from its own motion. It's the addition of those two things. And how do we add vectors? Think of them as displacements. One displacement plus the other. We end up over there. So if we want to express this as a vector, it's just u plus v. And we have u and v. So we have 0I plus 20I is 20I. And we have 300j plus 20 square root of 3j is 300 plus 20 square root of 3j. Please, 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 please. This is not 320 times the square root of 3. That's not how this works. Okay. Now, that's it. Okay. I don't know why I thought there was more to that problem. As long as we recognize that the true velocity is the addition of these two separate vectors, okay, it's not terribly difficult. The next part is more interesting. And I know I said that for part A, but now it's really interesting. So what is the true speed and direction of the airplane? Because like we just said, it's not just going north. at 300 miles per hour. The wind is pushing it, so it's affecting its speed and it's affecting its direction. So the true speed and direction, that's going to be the magnitude and the direction of the true velocity vector, w. So true speed, that's the magnitude of vector w. Okay, how do we find magnitude? Square root of a squared plus b squared. And we plug all of that into a calculator and we get approximately 335.24 miles per hour. True direction, well, that's theta, this theta. What is the actual direction of vector w? Well, tangent of theta equals b over a, opposite over adjacent. Okay. Now in this case, a is 20 and b is 300 plus 20 square root of 3. So to solve for theta, we take the inverse tangent of that messy fraction. Okay. And in this case, I kept it in degree mode. We usually express bearing and direction in degrees. And I got theta is 86.58 degrees. Please include the degree sign. So our direction, if this angle right here is 86.58 degrees, then the plane is actually moving in the direction of north, and then it's turning 3.42 degrees to the east. And yes, I do want it in this form. Keep things consistent with what we've studied before. So this is a really interesting problem because, I mean, if you think about it, this is how we actually calculate the flight plans of planes. We know that the plane needs to go from here to here. It's not just going to go in a straight line in that direction. There's wind, there's the speed of the plane we have to take into account. So if the wind is pushing the plane up, if we just went in this direction, then we'd end up way far north of where we wanted to go. So we take our vectors and we take all of that into account when we're calculating the plane's flight path. Okay. So the plane isn't just moving at 300 miles per hour. Part of that wind is pushing it north also. We're moving at 335.24 miles per hour. Okay. This also helps explain why if you're flying into the wind, your trip ends up taking quite a bit longer. Okay. And our direction is not just north, like we said. That wind is pushing it a little to the east, so it ends up going this way. So I love these problems. Please expect a problem like this on an exit ticket or exam. The only other thing I'd like to do today is one more simpler example, okay? Not one that's not quite this long. On the next page of our mastery sheet, guided notes. I call guided notes mastery sheets in AP Calc. A jet is flying in a direction of 50 degrees northeast. So let's rewrite this again, how I would express it too. So 50 degrees northeast, yeah, that's like in this direction. I would express this as north 40 degrees east. North, and then turning 40 degrees to the east. All right. With a speed of 200 miles per hour. So let's call this vector v. That means that vector v has a magnitude of 200 miles per hour. Find the north and east components of the velocity. So that's just asking us to find a and b. So our east component is our horizontal component, a, which equals the magnitude times the cosine of this angle, 50 degrees. Plugging all of that into a calculator and rounding to 2 decimal places, we get 128.56 miles per hour. The north component of this vector, that's our vertical component, b, which is the magnitude times the sine of the direction. 200 times the sine of 50 degrees, which is about 153.21 miles per hour. So, I mean, this is an incredibly important concept if you go on to study physics, particularly. It's something we return to in calculus as well, at least in the BC course. But if we're talking about something's motion, we need to be able to break it apart and describe, well, how much of that motion is actually going in this direction versus this direction, okay? And vectors, using these formulas, these trig formulas that we've studied for a few units now, it's pretty straightforward. Tomorrow we'll go through a couple more examples from our guided notes, and then Thursday we'll practice and take an exit ticket. Please remember to submit your exit ticket today by midnight. In addition to starting the 7.4 independent practice, it's very, very, very important, especially now that you're working on that on your own. Please reach out to me if you have any questions, join our Google Meet. Otherwise, have a good day. All right, well, I hope that was informative for you. Continue to reach out to me with any of your questions or concerns. Yes, Shelby, it's okay if you have questions, just reach out to me. You too, Arter. And I'll see you tomorrow.